Problem is all unique permutations of an array. This is a median level problem. It is given that the problem says, given an array of length n, find all possible unique permutations of the array in sorted order. A sequence A is greater than sequence B if there is an index I for which I j is equal to B of j for all j less than I and A of I greater than B of I. We are given an array and we have to give them set of permutations which are unique and also in sorted order. In the test case we can see that we are given an array 1 to 1 and in the output we can see the permutations are unique also in order. Similarly for the test case 2. So we get an array and we need to find permutations and then return the unique ones also in order. So looking at the constraints are pretty small because we are finding the permutation. So n factorial is the bare minimum complexity. Also the expected time complexity is n into n factorial. The time space complexity as well. For storing the permutations we will get the n factorial and the n space complexity. So that is the space complexity of the answer array, we can say. Okay, so the constraints are pretty small because it's a factorial kind of problem, and we need to, if we figure out all the factorials for the array including the duplicate ones, and then we can place them in an array, and then we can sort the array and then remove the duplicates. We can go by that method as well. Time complexity of that method will be n factorial for finding the permutations, right? N factorial, then placing them in the vector and all will take n into n factorial, and then sorting them will take that into log of the n into n factorial. So then we will go by removing the duplicate ones. So if we go by that method, finding all the permutations and then storing them in a vector and sorting, it will exceed the expected time complexity. Okay, so we need a better method. So what we can do is, while finding the permutations, we can use some pruning technique. We can, using some condition, we can remove the duplicates. Also we can take care of the ordering, so we will not need the vector and sorting at the end. So what we can do is we can sort the array in the beginning, like I have done here. We sort the array in the beginning, and then this is the answer vector. We made a helper function which is the recursive function. In the recursive function I'm taking the answer array, the index, the vector array, well, the index, and this is the base condition here. And in the remaining for loop, I'll tell you, we can take an example to show it. I took a test case. It was a 1 1 2 2 and 3 3. It is in sorting order. When I'm at the 1th index, when I'm at the 0th index, when I'm at the 0 index, I can swap with this index only, so I will get this array. Then I can swap with the next element, but that will give me a repeating array, right? The resulting array will be 1 1 2 2 3 3. So that is the wastage. We won't like to do that. So now okay, so if I take the index as 0 and I as 0, right, if I is 0, I'm swapping with the same element, right? I'm swapping it in the same element, so I can move ahead and the index can get 1, and then I will continue. Then again it can continue and I can reach the base condition. Okay, if I get I equal to 2, and I will check in the while loop. I is 0 and the array of I plus 1, which is here the value is 1, is equal to the previous value, right? So I don't wanna swap with this one with the I is equal to 1, so I will directly increase my I, so it will become 1, and then with the for loop it will become 2, so I will directly jump at 2. So at 2 I will swap at 2 and the new array will become 2 1 1 2 3 3, right? So I skipped that thing, and because of that I will not get a duplicate array. So this is for removing the duplicate array situation. And again for keeping the order, I have put this for loop. For example, if I want to swap 1 with a 3, the resulting array could become 1 1 2 2 3 3. If I swap a 1 with a 3, it will become 1, this will become 3, right? So it has removed the order. Now things are not in order. But if I do, 3 has to be here, right? 3 has to be here, but the rest of the array has to be ordered so that we can maintain the order in the output. So this thing has to be in order. So what will I do? We will copy this array, all these element will shift back, and this 3 will come here. This is my new array now when I swapped this one with this 3. So now we will go ahead with this array, and it will again give me new permutations. For example, first permutation will be this. What would be the next permutation? 1 1 2, and now this 2 will swap with itself, right? So it will give me same array. Now this 2 will swap with the 3. So what will I get here? 3 2 2. Right, this will swap with this. Okay, now this 2 will swap with 3, because if it is the recursion, right? This 2 will swap with this 3, right? First this will end its all of its recursive things because it will hit the base case. Then this thing, to hit the base case, it first will swap with itself to give this array, then it will swap with 3 to give me this array. Now it has reached its base point, this index has reached its base point. Now we will get an array where this 2 will swap with the 3, giving me this. It has reached its base condition. Then this 1 will swap with itself. Then this 3 will swap. 3 has reached its condition, right? This 1 will swap with the 2. Now the array will become 1 2 and 3. Right, now we will get right now this 1 which has swapped with 2, now it will swap with 3. No. Now this 1 will swap with the 2, and so on. Now you can see that the order is maintained. To maintaining this order, we have wrote this for condition. What it is doing, that if a 1 is swapped with a 3, the rest of the number will not get jumbled, because 1 is getting way later in the line, because 2 and 3 are already in front, so the order is disrupted. We will take 3 in front, and all the remaining elements till this index I where 3 was will be ordered. So this for loop is for that, and the other for loop is for reversing the order, because we are doing a backtracking here. So the algorithm overall is backtracking algorithm for finding all the possible permutations, but we have taken care of the ordering as well as the uniqueness in itself, the recursive thing. So we are not doing any extra part later, we are pruning the duplicate permutations within the recursive function. That was the overall idea, and the time complexity is n into n factorial. The n factorial calls to this, n into n factorial calls to this thing, and the n for including this for loop, the overall time complexity is n into n factorial. Yeah, this solution got accepted. Overall algorithm was backtracking. Okay, thank you.